to introduce Carles Bivià of the Universitat Politécnica de Valencia. He's going to speak on the special closure of polynomial maps and global non-degeneracy.
Thank you very much, Raúl. Well, first of all, thanks to the organizers for the opportunity of giving a talk in this workshop, and also felicidades, Federico, por tu trayectoria y por esos espléndidos 60 años, ¿no? Let's continue in English. Let's continue in English. So, I'm going to speak about some basic questions concerning polynomial maps. So, the motivation of my talk is the study of a kind of extension of the notion of integral closure for polynomial maps, and also to have a look to possible applications to the notion of index of a polynomial vector field in the real case. So I have to start from very algebraic notions in order to understand our definitions. So this is part of a joint work with Jorge Huarcaya, and this is also part of a recent paper that I have published. We have published in Mediterranean Journal of Mathematics. So let's start. So I'm going to start with the definition of integral closure. So when we fix a ring R and we fix any ideal I in R, so we say that H is integral over I when H satisfies a relation of this type. So this is the definition, and it seems that this is going to be a very complicated object, but you will see that this is let's say this is a notion which is going to be very useful both in singularity theory and commutative algebra. So when we consider all the elements H belonging to R such that H is integral over I, what we obtain is the integral closure of I, and this notion can be also generalized for modules. So I am going to denote the integral closure of I by I bar. This is going to be denoted by I bar, and it's always true that I is contained in the integral closure of I, and this is always contained in the radical of I. As I say here, you can see that there are many words which are related with the notion of integral closure, both inside commutative algebra, as you can see in the work of Huneke, Swanson, Vasconcelos, Ulrich, Gotot, and you can also see the applications of the notion of integral closure in singularity theory in the works of Bernard Teissier, Gaffney, and Kleiman. Well, the computation of the integral closure of an ideal is something which is let's say non-trivial. This is non-trivial, but there is one case when this is completely possible. This is the case in which the ideal I is monomial. So let's fix coordinates x1, xn in Cn, and let's fix any ideal I which is monomial. Monomial says that I admits a generating system which is formed by several monomials. I'm going to denote by xk. I'm going to write x to power k to denote the monomial x1, k1, xn, kn, whenever k is this vector belonging to Zn. So it's possible to prove, and it's well known, that the integral closure of I is equal to the ideal generated by those monomials x to the power k such that k belongs to the Newton polyhedron of I. So the Newton polyhedron of an ideal, this is defined as follows. Let's define this first for the monomial case. So let's suppose that let's put an example. Let's put an example. Let's suppose that I is the ideal which is generated by x to the power 5, and let's put here xy, and let's put here y to the power 7. This is an ideal which lives in O2, O2, which is the ring of convergent power series in the variables xy. So we have that the Newton polyhedron of I, this is equal to the following. The Newton polyhedron, which is going to be denoted by gamma plus of I, this is equal to the convex hull, this is equal to the convex hull of this set. The set which is given by 5 0 plus R2 with 1, 1 plus R2 plus, and let's put here 0, 7 plus R2. This is a very well-known definition. Well, let's say this is the union of this and this and this. Let's consider the convex hull of this, and what we obtain is something which could be drawn as follows. And let's put here xy. So this is this quadrant together with this quadrant, and let's put here the other quadrant, and let's consider the convex hull of this region. And what we obtain is this region. This is an unbounded region. So this can be done for any monomial ideal in On, and this can be also done for any ideal in On. I mean, let's suppose that f is an element of On, and let's suppose that the Taylor series expansion of f around the origin, this is written as ak x to the power k, where for some k. So let's denote by, well, let's call the support of f. This is equal to the set of those k such that ak is not 0. ak is not 0. This is the definition of the support. And I'm going to define the Newton polyhedron of f. This is equal to the convex hull of those elements which are written as follows. We have that the Newton polyhedron of f, this is equal to the convex hull of this set, of the union of this set k plus Rn bigger than or equal than 0, where k belongs to the support of f, to the support of f. When we have any ideal I, living in On, the Newton polyhedron of I, this is equal to the convex hull of the union of the Newton polyhedra of the functions belonging to the ideal I. So this can be done in O2, in On, not only in the monomial case, and we can do this for any ideal in On. So what is known is that when we have any ideal I, which is monomial, what we have is that the integral closure of I is equal to the set of those x to the power k, such that k belongs to the Newton polyhedron of I, which is something very nice. It's always true that when we consider any ideal I of On, and if we denote by I0 is the ideal generated by all monomials x to the power k such that k belongs to the Newton polyhedron of I, it's always true that I is contained in I0. This is always true. So when we have any... Is it possible to erase this? Is it possible to erase this? Okay, thank you. So let me consider any ideal I. Let's consider any ideal I which is living in On. So what we can consider is the Newton polyhedron of I. We can consider gamma plus of I, which is the Newton polyhedron of I. And let me have a look to I0. I0, this is equal to the monomial ideal x to the power k, such that k belongs to the Newton polyhedron of I. It's always true, it's obvious that I is contained in this ideal. So what we have is that I is contained in I0, so the integral closure of I is contained in the integral closure of I0. And a very natural problem is to, since this is monomial, this is equal to I0 again. This is equal to I0 because of the fact that I0 is a monomial ideal. So a very natural question is to have a look to which are the cases in which this is equal to this one. This is a very natural problem. So the computation of the integral closure is something difficult. In the monomial case, this is easy. So when we have any ideal I, this is always contained here, which is always monomial. So a very natural problem is to characterize those ideals I such that this is equal to this one. And this was done by Marcelo Saya in 1996 in the Journal of Algebraic Geometry. So when we consider any ideal in On, so we have the following equivalent conditions. We have that the integral closure is equal to I0, and the other condition is that for any compact phase of the Newton polyhedron of I, we have that this system has all the solutions contained in the union of the coordinate planes. Let me define this. So I'm going to give the definition of these polynomials. So the definition is very easy to understand. When we consider any analytic function f, which is equal to ak x to the power k, and when we consider any compact subset, let's consider delta. Let's suppose that delta is a compact subset of Rn plus. I'm going to denote by f delta, this is equal to the sum of those ak x to the power k, such that k belongs to the set delta. This is equal, let's say this is equal to the restriction. I mean, let's sum only those monomials of f belonging to the set delta. The ideals satisfying this are called Newton non-degenerate, and are also called ideals with maximal integral closure. So, in the proof of this result, it is fundamental the application of the characterization of the integral closure in the analytic category. And this is a result due to Lejeune and Tessier. So when we consider any ideal I of O(n), if we suppose that I is the ideal generated by these elements, then saying that H is integral over I is the same as saying that there exists some constant C and an open neighborhood U of 0 in Cn, such that this relation holds for any point x belonging to the neighborhood U. So let's come back to the definition of integral closure. This is very algebraic. Wait a minute. This is very algebraic. And this characterization is very analytical, which is a nice bridge. Nice thing. Let's continue. So this characterization has been the motivation for us to the introduction of the notion of special closure of a polynomial map. So let's have a look to the following definition. When we consider any polynomial map f from Kn to Kp, and we consider any polynomial, so we say that H is special with respect to f when this analytic inequality holds for some constant C and for all big enough x, which in some sense could be, we can say that this is a global dual notion of the notion of integral closure, but in a global context. So we are going to denote by Sp of f. This is the set of those polynomials which are special with respect to f, and we will refer to Sp of f. This is the special closure of f. What I have to say also is that the Sp of f is no longer an ideal. This is a semi-group. On the other hand, I am going to note by bold S of f. This is the set of those k such that x to the power k is special over f. So one of the objectives of this talk is to show a result parallel to the characterization of ideals with maximal integral closure in the framework of polynomial maps and special closures. Well, there is a technical lemma here, and let's see some examples. Let's see some examples. So by Saya's result, what we have is that I bar is equal to I0 if and only if for any compact phase of the Newton polyhedron of I, for any compact phase, any which is a compact phase of the Newton polyhedron of I, what we have, well, let's suppose that I is the ideal generated by G1GR. So what we have is that this is the same as saying that the set of solutions x belonging to Cn such that G1 delta acting over x is equal to GR delta over x is equal to 0. This is contained in the union of the coordinate planes, x belonging to Cn, such that x1, xn is equal to 0. So what we want to do now is to establish a parallel result when we fix a polynomial map germ. Let's have a look to the following. Let's fix an f from kn to kp, where k is equal to r or c. So we can replace the integral closure. We can replace the integral closure by the special closure, and we have to replace this by another object, which is the right object. So I'm going to replace this by the special closure of f, and I'm going to replace this by the following. I'm going to define the global Newton polyhedron of f. This is going to be defined in the following way. I'm going to denote this by gamma tilde plus of f. This is equal to the convex hull of the union of the supports of the component functions of f, support of f1, support of fp, together with the origin. This is the definition. So let me consider the following map. Let me consider the following map from C2 to C2. For instance, let me have a look to the map which is defined by xy. Let me consider xy, and let's associate to this point xy. This is the point x2 plus y2, and let me have a look here to the monomial x5, y5. So what we have is that the usual Newton polyhedron of f, this is equal to the following. We have that the Newton polyhedron of f, this is equal to the convex hull of this with this, and these quadrants, and this quadrant, and this quadrant. So what we have is that the Newton polyhedron is this unbounded set, all this. And the global Newton polyhedron is the following. Sorry, let me put here f. And the global one, this is equal to the following. This is equal to the convex hull of this monomial with this monomial and this monomial too. So in some sense, we can say that in the local case, this is absorbed by this. But in the global case, this monomial counts. So what we have is that this is 0, 2 to 0, and we have here 5, 5, and we have this. This is equal to the convex hull of this with this and this. So what we have done, and also the origin. So what we have is that this is equal to this one. Good. This is something which is different from this one. This is compact. This is not compact. Non-compact. So I'm going to put here, what's the right thing to be put it here? One could be tempted to say that this has to be substituted by those monomials belonging to the global Newton polyhedron. But we have to take care because of the following. Let's consider here f, a function which is from C2 to C, which is such that xy, and this is equal to xy minus 1, which is the global Newton polyhedron in this case. What we have is that the global Newton polyhedron is going to be the following thing. So we have here the monomial xy, which corresponds with the point 1, 1, and this corresponds with the point 0, 0. So the global Newton polyhedron of f, this is equal to this. This is equal to this. We have a monomial here, xy, and we have another monomial here, which is called 1. By by Martello-Sayas result, what we have is that this is equal to this one if and only if for any compact phase this is true. We have to replace this by another condition. And the natural condition by Kuznetsenko's result is to say that something similar happens for any compact phase not passing through the origin. So we can put here something, and we can inspire ourselves by Kuznetsenko's result we can substitute this condition by a condition which depends on the phases of the global Newton polyhedron that do not contain the origin. But this is non-degenerate, and this is not spatial, and this is not spatial too. This is a problem. So the extension of this scheme is not so straightforward. Okay? So, well, another case is the example which is given by this map. Let me consider here the map which is given by, okay, what we have is that there is another example. There is another example which is given by the polynomial map, which is given by only one component, which is given by this, x squared, y squared. And what we have is that, well, let's consider here f from C2 to C, and let's put here xy, and let's associate to this point the point x squared, y squared. So the Newton polyhedron of f is equal to the convex hull of the support with the origin. So we have something of this sort also. But this monomial here, which is, this is the point 2, 2, and this is the point 1, 1. It's possible to prove. By this lemma, it's possible to prove that this is not special over f. And this is a bit disappointing, right? So what we have is that xy is not special over x squared, y squared. I mean, what we want is to capture those monomials which are special with respect to f. And we thought that all the monomials corresponding with the points with integer coordinates belonging to the global Newton polyhedron, we thought that they were going to be the right ones, but it is not true. It is not special over this. So, which is the right version? First of all, what I would like to say also is that when we consider any polynomial map, and we consider the set of those monomials which are special with respect to f, this is always a convex set. It is a good thing. And on the other hand, it's always true that when we consider any element which is special with respect to f, the support of h is always contained in the global Newton polyhedron of f. In particular, what we have is that S of f is contained in the global Newton polyhedron of f. So let's, I would like to introduce also the notion of multiplicity of a polynomial map. So let me consider a polynomial map f from Cn to Cn, and let's suppose that and let's denote by I of f the ideal generated by the component functions of f. So let's suppose that the zero set of f is finite. So we are going to define the multiplicity of f, which is going to be denoted by nu of f. This is the definition. This is the dimension as a complex vector space of this quotient. It is well known that this number is equal to the sum of the multiplicities, of the local multiplicities of those x belonging to the zero set of f, where O and x denotes the ring of complex analytic function terms from Cn x to C, and Ix of f is the ideal of O and x, which is generated by the germs at x of the component functions of f. So there is a number. So this is a number which is associated to any finite complex polynomial map. This is very important because of the following. So we were able to prove that the elements which are special with respect to f satisfy an important condition with respect to multiplicity. So when we fix any complex polynomial map, which is also finite, saying that h is special with respect to f is equivalent to saying that there exists some delta such that for any alpha belonging to the ball centered at 0 with radius delta, this map, which is f plus h alpha, is a finite polynomial map, and they have the same multiplicity, which we can say that this is an analogous in the global case of the Riesz multiplicity theorem, which is a very deep result in computative algebra. So we can we can establish a kind of parallelism between the risk multiplicity theorem and this result. Well, let's continue. Let's fix any complex, any polynomial map, from Kn to Kp, and let's denote by d the degree of f, which is equal to the maximum of the degrees of the component functions of f. So let's introduce a new variable, and let's denote by h star the homogenization of h with respect to this extra variable. So when we have any polynomial map, what we can also consider is the f tilde, which is the homogenization of f of degree d by means of the extra variable xn plus 1. So we have the following proposition. Let's consider a polynomial map f from Kn to Kp, and let's denote by I the ideal of a Kn plus 1, which is generated by the component functions of the homogenized map. So there is another ideal upstairs. So it's possible to prove that when we take any h such that the degree of h is at most d, and if we denote by h star the homogenization of h, it's possible to say, it's possible to prove that h belongs to the set of special polynomials of f1 if and only if h star belongs to the integral closure of I. So we have a kind of complete dictionary. So let me have a look to this. I'm going to put here not only f. We put here f together with 1. And this is the point. So we have to put here f1, not only f. So what we have is something like this. Let me consider a Newton polyhedron of a map. Well, let me consider here f from K2 to K2. And let's suppose that the Newton polyhedron of f is something which could be drawn as follows. Let me consider here this point, and this point. So let me consider here f tilde, which is a map from K3 to K3, which is given by the homogenizations. We have here x, y, z. This is going to, well, let's suppose that f is equal to f1, f2, and let's suppose that d is equal to the degree of f, which is equal to the maximum of the degrees of the component functions. So let me put here f star 1, and let me put here f star 2, and this is x to the power 3 to the power x3 to the power d. So what's the relation between the global Newton polyhedron of f and the Newton polyhedron of the ideal generated by this component function? So what we have is something like this. This is the z-axis, the y, and the x-axis. Let's draw this here. So we have something like this. We have something which is like this. And let me have a look to the Newton polyhedron of this. So this is the global Newton polyhedron, which I'm going to draw here, gamma plus f. And let me put here x3 to the power, sorry, this is z, right? This is z, excuse me. This is z to the power d. Let's put here z to the power d. So we have that the Newton polyhedron is something which is of the following. This is not the best possible picture, but anyway. Wait a minute. Let me put here this and this. No sé lo que es peor. A ver. This is the Newton polyhedron of the ideal I. The local version. I mean, what we have here is the global Newton polyhedron, and what we can consider is the local Newton polyhedron of the homogenized ideal, which is something that is unbounded here, unbounded. Okay? So, saying that H is special with respect to F, this is the same thing as saying that the homogenized map of H is integral over this. So we have a kind of dictionary. Okay? Let's continue. So the right version of such a result is the following. Let me consider a polynomial map and let's denote by d the degree of f. So we have that the following conditions are equivalent. We have that the set of special monomials of f1 is equal to those monomials x to the power k such that k belongs to the global Newton polyhedron. The other condition is that f tilde is Newton non-degenerate, and the other condition is that for all phases delta of the global Newton polyhedron not containing the origin, this inclusion holds. So this condition is condition C. This element here is contained in A, and we have obtained that the right object here is not SP of F1, of F, it's F1. This is the right object to be put it here. This is the right object. So, if any of this condition holds, so we say that F is Newton non-degenerate at infinity, or that F has maximal special closure. In the convenient case, convenient means that the global Newton polyhedron intersects each coordinate axis. This is the definition. Okay? So if we suppose that F is a convenient polynomial map, we can put here SP of F, not SP of F1. So we need to suppose that F is convenient in order to replace F1 by F. Well, as a consequence of this result, when we have any convenient polynomial map, and we suppose that real convenient polynomial map, and we suppose that F is non-degenerate at infinity, if we suppose also that the zero set of F is finite, what we have is that the index of F is equal to the index of F plus G, where G is any polynomial map whose support is contained in the interior of the global Newton polyhedron of F, which means that the principal part of F is equal to the principal part of F plus G. I mean, when we consider any polynomial map which is convenient, let's suppose that F is a map from Rn to Rn, which is a polynomial map. What we can consider is the Newton polyhedron of F, the global Newton polyhedron of F, which is something which could be drawn in this way. For instance, this is equal to the complex hull of the support of F with the origin. This is a compact set. So let's suppose that F minus 1 of 0, this is finite. So we can speak about the index of F. The index of F, which is defined as the sum of the topological index at X of F, where X belongs to the zero set of F, sorry. So when we have any polynomial map which is finite, what we can consider is the index, which is equal to the sum of the indices at those points X where F is 0. And what I say here is that when we consider monomials here, and if we suppose that F is Newton non-degenerate at infinity, what we have is that the index we have is that the global index of F is equal to the global index of F plus G, where this G is contained in the interior of the global Newton polyhedron of F. This is a global counterpart of a known result of Gutiérrez-Ruas in the local case. Let's fix a convenient global Newton polyhedron, and let's suppose that F is a polynomial map from Cn to Cn such that the support of each component function is contained in gamma plus. It's always true, so it's possible to prove that the multiplicity of F is upper bounded by n factorial times the n-dimensional volume of the Newton polyhedron. This is known, right? What is not known is that the equality holds if and only if F is Newton non-degenerate at infinity, and the Newton polyhedron of F is equal to the global Newton polyhedron that we have fixed from the beginning. So it's always true that when we have a polynomial map, what we have is that the multiplicity of F is less than or equal than n factorial times the n-dimensional volume of the global Newton polyhedron of F, and we can obtain a complete characterization of those polynomial maps for which this is equal to this one. And these are the maps which are Newton non-degenerate at infinity. So we can summarize what we have said in the following results. So when we fix a map which is convenient, which is a convenient polynomial map, then the following conditions are the same. Saying that F is Newton non-degenerate at infinity, this is the same as saying that the set of monomials which are special with respect to F are determined by the global Newton polyhedron. This is the same as saying that the set of those polynomials which are special with respect to F are contained in the global Newton polyhedron. And in the complex case, this is the same as saying that the multiplicity of F is equal to n factorial times Vn gamma tilde plus of F. So to end, let's have a look to some corollaries. When we have a function when we have a polynomial function from Cn to Cn, and we fix the global Newton filtration, which is determined by a fixed global Newton polyhedron, what we have is that the multiplicity can be upper bounded by this function of the degrees of the component functions with respect to the fixed global Newton filtration. So there's a result which is due to which can be seen in two different ways. I'm going to write here. So when we have a function, a function f from Cn to Cn, function f from Cn to Cn0 to C0, let's suppose that f is analytic. F is an analytic function here, analytic, and let's fix a vector w which is equal to w1, wn belonging to Zn bigger than or equal than 1. Let's consider a vector of weighted. This is a vector of weighted. This is a vector of weights. Vector of weights. So Tomari, Furuya, they proved Furuya. What they proved is that the minimum number of f, is bigger than or equal than d minus w1 multiplied by d minus wn over w1 wn, and equality holds if and only if the principal part of f with respect to this vector of weights has an isolated singularity at the origin. Pw of f has an isolated singularity at the origin. So what we have obtained as a consequence of the previous result, what we have obtained is something similar in the global case, which means that when we have a function which is a polynomial map, what we have is that the Milnor number at infinity is upper bounded by this fraction, and equality holds if and only if the principal part of f in the global sense has isolated singularities, which is a global counterpart of the result in the complex case. So that's all. Thank you very much.
Any questions, comments?
Just some comments. First, the local case, the result for this is of monolaric, and you are giving the counterpart of.
No, this is the, well, if the principal part of f has an isolated singularity, what we have is that this is equal to this one, which is known, but the converse is the new thing. Huh? I mean, this is known, and this result is due to them and our result too. Do you remember that we did we did something similar, not only for gradient vector fields. We did the same thing for any vector field from Cn to Cn, not only in the weighted homogeneous case, we did that for any Newton polyhedron filtration.
Just another comment that as a consequence of this work, you have the counterpart of the famous result of Damon about the semi-quasi-homogeneous constancy of lunar number. And if you are in these conditions with a quasi-homogeneous number, when you define by terms which are below the Newton polyhedron, you have the constants of the lunar number in this case. So it's a counterpart of the famous result of Damon's on semi-quasi-homogeneous case, just to remember.
Okay, that's right. Yes. Thank you. Okay. I see.
Comments? Questions? Then it's time to speak.